Alright, so apologies for the last video being so short, um, but I wanted to give this its own time frame as well. So what we're going to do in this one is we're going to start talking about different types of polynomials and how they can be modeled in different behaviors. So in this activity, we're going to be given different scenarios using polynomials. What degree of polynomial might there be? Alright, so choose the verbal descriptions that would best model by polynomials. The population is protected. The population of a protected fish in a pond as a function over time. Well, this one, polynomials are more about multiplication. So this one probably wouldn't be the best. Now, and there's no exponent. Now, this could be exponential, and just to be clear, exponential is when something grows over time, meaning that the exponent is the x. We don't have x to a power. So it could be an exponential, but I don't know if it's appropriate to consider it a polynomial. Volume of a globe as a function with the radius. This means that we're going to have volume, and the formula for volume, you don't really have to be familiar with it, but you know it is related to radius to some power. So this is saying that the r's are input in this case. So this one would be a polynomial mainly because of the fact that we have this r as an input and it's being raised to some power, some number here. Okay, so let's see what we got here. The average weekly cost per shoes for a store for a shoe company to produce running shoes. So the average weekly cost. So average, I feel like this is going to be over some amount of time. So this isn't so much an exponential because it might have something like this. So it's not really having x x to a power. Again, I could be wrong. I might be interpreting these wrongs. So the price of a stock market that fluctuates times throughout the years. So in other words, a stock market price where it's going like this. Now this does look like an exponential. It looks a little weird. We might not be familiar with how we do it, but this to me feels more like an exponential. So I'm gonna go with these two as, or I'm sorry, exponential. I just finished saying exponential and polynomials are the same. This is a polynomial, and it's fluctuating. So there's different, depending on the time, it might go up, it might go down. So these are the ones I'm assuming will be our answers. And it's correct. So we want to think about this as to some power. So you're trying to think of power. Like I said, this one is tricky because of the fact that it's an exponential, not a polynomial. All right, so let's look at this. Drag the tiles to the degree. So the degree is essentially the highest power that we're talking about. So temperature gets hotter in the morning and peaks about this time. Then it gets cooler around this time. When it warms up, it continues until midnight when the temperature drops sharply. So in other words, what's happening here is this temperature in the morning. So temperature gets hotter in the morning. So it's going to get hotter. It's going to keep going on, and then it's going to drop down. So to me, this feels like it's a quadratic. It's going to go up and then it's going to go back down if we're only talking about that period of time. At some point in time, it will go back up again, but I have a feeling they're only talking about these two periods of times, which is a parabola. It's a quadratic. Jim throws a ball at the height and from a ball increases until gravity makes it stop climbing and it goes back down. So this one could be it. So they're doing a few ones that are kind of contradicting each other. I'm going to read more into this one. Then it gets cooler until 8 p.m. When it gets warmer, the air again, then it continues warming until midnight when the temperature drops sharply. So let's see if I can redraw this one. The temperature gets hotter in the morning. So it's getting hotter and peaks about 2 p.m. And then it starts kind of going down when a warm front heats the air and then it drops back down. So it looks like here we have one curve, two curves, three curves, and four curves. So I'm going to say that's degree 4, a quadric. So make sure to read all of them. Clearly I didn't read all of it, so that was where the problem was. Let me erase all of this. This one, this guy's throwing the ball up. Gravity makes it come back down. That one is more of a parabola. So the issue here was this was a parabola, but it kept going, so there kept to being that increase and decrease. A car travels a certain distance over time, and it moves at a constant rate. So it's constant, like nothing's making it go up, nothing's making it go down. Anytime you hear the words constant rate, you want to think straight line. So that's going to be a linear polynomial, degree 1. Let's take a look at this one. Gross sales. Let's see here. So the gross sales at a restaurant pick up in January. So in January it goes up and slowly. Okay, so sales. So at first it was low, then it picks up in January, and slowly increase throughout March. So that could be another one. It's phrased very weird. The restaurant owner sees a decline in sales in April, but steadily increases in May and continues until it peaks in July. Then it decreases until December, when it begins to slowly increase again until the end of the year. So here I'm counting, depending on what this is. This one is either 1 or 2, depending on how they're phrasing it. This one is 3, 4, 5, and at least 6. So this one might be a 1, making us go only to 5. And it has to be 5. So I'm not sure why they said it picked up in January and then said it kept increasing, because that clearly had no effect on its degree. So that was just very weird. It pick up in January and slowly increase until March. So that just means from this, they might have started keeping track in January. That's very weird how they phrase that. A toy car is rolling in around. Well, we know it's going to be degree 3, but let's see why. Why is this degree 3? Height. So rolling, the height of the ramp depends on the time interval, then increases as it goes up the hill, then decreases as it reaches down the hill. So it's rolling up a ramp. So it's rolling, a car is rolling along a ramp. The height of the ramp drops over time, then increases as the hill goes up. So I'm guessing it's going like this, and like this, making it 1 curve, 2 curves, 3 curves. All right, so let's see if I misinterpreted any of those. So the hardest one I think was probably this one. Let's go a little bit more into this. So describe the restrictions that might make sense in these scenarios. The price of a stock fluctuates several times throughout the year. So I would say a domain restriction. Domain restriction is X must, or X must be greater than 0. Because there's no such thing as negative time, range is also greater than 0 because there's no such thing as negative money. There's this thing if you borrow money to buy stock, but that's not related to the stock price. Must be greater than 0 because there is no negative time. It also depends because of the fact that if you're keeping track of something before you bought the stock or before you started keeping track of it, but if it's before you started keeping track of it, there shouldn't be a function for it because you don't know what the value was. So range is greater than 0. There is no such thing as negative money. So I didn't do this for the last one, but I'm going to call this number 2. I should have called the other one number 1. A ball hits in the air and raises until it reaches the high point. Then it falls to the ground. Y cannot be greater than 0 because that is the ground. And X cannot be, I put Y cannot be greater. I meant to say less than. Cannot be less than 0 because that's the ground. X cannot be less than 0 because no negative time. Because there is no such thing as negative time. Let's do volume. Increases and the balloon decreases. I feel like all of these are X and Y cannot be greater than 0, so I'm just going to say that. X and Y cannot be less than 0. I'm just going to say those. Let's see if they go into more detail. Time is bounded below 0. So basically the same thing. We can't do anything less. I'm going to give myself a 4. The question with January seemed like there would be another curve. All right, so I'm going to do that. So basically, that's what we're talking about when we're talking about key features of functions, polynomial functions. We're talking about the curves. So this is what I mean by the curves. Here's a minimum, here's a maximum, here's another minimum. And later you'll learn about absolute minimums, which this is the absolute minimum. Nothing will ever be smaller than this. And a local minimum, meaning that this is small, but it's not the smallest. Zeros tell us once we go from positive to negative. These are usually important because let's say a company is in the red, meaning that they're paying more money to run the company than they're making, or they're in the black, meaning that they are making money. Okay, and relative min and maximums. It's weird that they don't call this a relative minimum and this a relative maximum, but they do acknowledge it here. So make sure you're reading this. Average rate of change. So average rate of change is when we take 2 points and we calculate the slope in between them. That's going to be our average. All right, so when we're looking at something like this, a cylinder and its volume. So let's talk about what the features in this are. So here, our extrema, meaning our minimum to our maximum, our extrema are these 2 points. These are our extremes. So those are 2 features there, local min and local max. Our zeros are where we're going to go from positive to negative. And then we're going to be talking about the behavior. So looking at this graph, as x goes to infinity, that means as x is going to the right, f of x, our y value, is approaching negative infinity. That means as we go to the right, our graph goes down. The next one is as x approaches negative infinity, that means, you know what, let me write that in a different color so it makes a little more sense. As x approaches negative infinity, x approaches negative infinity, our f of x, our y value, f of x, approaches positive infinity. That means our graph is going up. So that's what this means. Whenever we're talking about our end behaviors, we're going to talk about there should be one where it's x is going to positive infinity and another one where x is going to negative infinity. And all that means is positive infinity, as x goes to positive infinity, we're going to the right. As x approaches negative infinity, we're going to the left. And we're just going to talk about what happens. Well, as we're going to the right, we're going down. And as we're going to the left, we're going up. And that's when we're going to talk about polynomials with powers and things like that. So I might have referred to this before when we were talking about end behavior. So this will hopefully help clear that up a little bit. Then we're going to talk about bindings, meaning something like, for example, well, we can't really have a negative radius, so this can't work. None of this can work. And we can't really have a negative volume, so this can't work, this area right here. So that's what it means by bounded. We're bounded by certain behaviors. So because of that, we can't have this extrema anymore, this minimum. We can still have this part, and we can't have a lot of the zeros. And the reason why they crossed out all the zeros is because, well, this is where it exists. We can't really have a 0, 0. It just doesn't exist. And over here, we wouldn't have anything that exists either. So there are no zeros because we want everything to be positive, not 0. Next feature is when it's increasing or decreasing. So this is where you might see where I was counting the curves. One curve till it decreases, another curve as it increases. It's starting to increase slower, but still increasing. Right here, our peak, it's no longer increasing, it's just going to decrease down. So that's where you see me counting the shape. So if I count here, I see one curve, two curve, you can barely see it, but it's starting to decrease, 3, 4 curve. There's 4 curves there. So let's see here. So they're going to locate our critical points, our points where this is happening. They call them extrema in this case. So this is our lowest point, so that's one extrema. This is our highest point for one, and this is our lowest point. So it decreased very little, but it did decrease. So 1, 2, 3, and 4. All right, now we're going to be talking about our zeros. Well, this doesn't have any zeros. It never touched the x-axis. But we can talk about our end behaviors. So this says, as we're going to the left, as x approaches negative infinity, so as we go to the left, our y is going to positive infinity. And this one's saying as x approaches positive infinity, as we go to the right, our y also approaches positive infinity. So this is an even polynomial. So if I counted the curves, I should have an even number. 1, 2, 3, 4. 4 curves. So you'll find that with an even polynomial, the end behaviors are the same for the left and for the right, no matter how many curves are in the middle. And for an odd polynomial, our end behaviors are going to be backwards. Linear is probably the best example I could give for a odd polynomial, because linear is one power. And like I said before, there's no x values here. There's no zeros, I should say. And are bounded, where are we bounded by? Well, it says a 7-year span, so we don't care about anything after 7 years. So that's where we're bounded by. We're bounded by here to here. And within that time frame, our y values are bounded from here to there. This is the highest point within the 7 years. This is the lowest point within the 7 years. So that's where we're bounded. All right, and the average rate of change. So let's say I want to find the change between here and here. On average, this is the change rate. Sometimes it's growing faster, sometimes it's growing negative, but for the most part, that's the average. So a lot of times we'll change, we want to do it in a line for a rate of change, just because that's easier to kind of predict. So we could be losing money in that period of time. We could be gaining a lot of money if this, for example, if this was a stock market, but it gives us an okay predictor of it. Ooh, sorry. So our next rate of change is looking at a chart, and we can find an average rate of change just by doing this minus this, and this take away this. That's known as our slope. You might have saw the formula in that last slide. X2 minus x1 is on the bottom. Y2 minus y1 is on the top. Because the reason for this is rise over run. What controls the rise? The y values. What controls the run? The x values. So that's all we're doing. If you want to find the average rate of change. So one of the ways we can find zeros is by looking at the y values. So see how these are all positive numbers. Well, from here we go to positive to negative. That means there has to be a zero somewhere in the middle. So from here we're going from negative to positive. That means there's a zero somewhere in between 5 and 6. This one was really obvious here because of the fact that 3 equals 0. So that was really easy to see, this positive to negative change. But here's a little more subtle. We kind of did this when we were approximating zeros, where we had to keep plugging in a smaller number. And if we got if we kept getting negatives, we had to keep going smaller and smaller and smaller. And then if we got a positive, then we had to make this number, or we had to make this number bigger, because if we're going from the bottom to the top. And if we had this number got positive, we need to make it smaller. So bigger because it was on the left side, smaller because it was on the right. And as we kept getting closer and closer and closer, so this being the left side, and on the other side, we kept getting closer and closer. I was supposed to change colors. We kept getting closer and closer and closer. Eventually, we would find that ideal zero spot. I felt this should have been included in Unit 4. That's really weird. All right, so here's what we're doing. What are we doing here? So this is what I mean. We're going to try to approximate that spot. So we're trying to find, so looking at this one, we can see our highest point and our lowest point. So we're being bounded for 6 years, from 0 to 6. So we need to find our lowest points and our highest points. They already nicely circled our zeros. This one, like I said, we couldn't see it. We just know it's somewhere between 5 and 6. And then this is what is our bounded, our highest point between the bounded time and our lowest point between the bounded time. So let's see what we're doing here. Find the extrema, our highest point and our lowest point. And this one, average rate of change. So we're saying the change between these two, are y2 minus y1 over x2 minus x1. That's what we're doing on this slide. All right, finding points, key points on polynomials. So let's get this worksheet. Done. So find the key points of the features that is, find the extrema. So the extrema is, so first let's figure out where we're bounded. That's probably a good feature. Oh, they're not asking us to find where we're bounded. And because they're talking about n behaviors, we're probably not going to find our bindings. So I'm going to say there are maximums at, and I'm just going to say the x values. So there's one at x equals 0, x equals 0, and x equals about, I'm going to say somewhere right in the middle, about 3.25. We're approximating it. There are minimums at, I'm just going to do the x values again, at x equals about 1.25. These maximums are 0 and 10 respectively. And what I mean by respectively, I mean in the same order. At 0, our y is 0. At 3.25, our maximum is 10, which is a little less than -3. So it's important to distinguish that the minimum is at this point, but that's not the minimum. The minimum is not x equals 0. The minimum is 0, this number right here. Just like this is a maximum of 10. When we're talking about the maximum, we're talking about this right here. And by the way, this is telling us like, oh, this is in 100 feet. So times 2,000 feet. Just because I feel they didn't do it. So it's about it's about 20,000. So I'm gonna do that. You can see how they wrote it. They wrote them as points. Honestly, it's probably a good idea. And I forgot to put my zeros in. I totally forgot to put my zeros and my n behavior in. So as x approaches negative infinity, if you want to use a symbol, you can use the equation editor. So I'm going to do this one as x. There's actually an approach symbol right here. Oh, but it has a little thing at the bottom. I wanted the arrow without something. So I guess I can just do it like this. As x approaches negative infinity. Where's the negative? And there should be an infinity symbol somewhere. Do they not have an infinity symbol? Wow. I cannot believe they don't have an infinity symbol here. All right. Well, then don't use this apparently. So as x approaches negative infinity, f of x, or you can say y. Don't forget your comma. Y approaches negative infinity. I didn't want to spell out negative infinity, so I'll just put negative infinity. Also, as x approaches infinity, so as x goes to the right, y approaches negative infinity. When does it increase? When does it decrease? Y increases from negative infinity to 0, as well as, what was our value here? About 1.25 to about 3.25 to about 3.25. Y decreases from about, y decreases from 0 to about 1.25, as well as 3.25 to infinity. So I'm just saying when it increases and when it decreases. So from negative infinity, from the beginning of time as far as we know, all the way until 0, it's increasing. And it's also going to increase from 1.25 all the way until 3.25. And then we're also going to talk about when it decreases. So it decreases from 0 all the way to about 1.25. And then it's also going to decrease from about 3.25 all the way down to negative infinity. Or all the way to positive infinity. We're talking about the x values, not the y values. I'm sorry. So from 3.25 all the way into infinity, this thing's going to decrease forever. They use these little symbols, but unfortunately, I didn't see that symbol, so we can't really talk about it. Interpret the key features in part A in some context of a problem. So we're going to talk about this. So I'm going to talk about like getting money and spending money. So John, we're going to talk about John never worked before being an adult. So in this case, 0 represents when John was an adult. When he turned 18, he bought things on credit. That's why he's going to be in debt for a while. Or, I guess I should talk about the actual thing. I guess. I was just going to make up a random story, but I guess we should talk about this. Two friends decide to go on a 4-hour road trip off-roading in a vehicle. The graph represents the elevation over terrain. So elevation. So before off-roading, the friends were below sea level. They got to sea level when they started off-roading, but this was at the top of a hill. About an hour and a quarter, because it's 0.25, in they climbed another hill. Which was about, what's our maximum? 20,000 feet. 20,000 feet. Because remember that 10 All these numbers represent 10 feet. 20,000 feet. I'm going to put a little comma here. They went down this hill until the end of their off-road trip. Because what's happening here is they're at below sea level, they climb up, they start rock climbing, or they start off-roading, and it's like, woof! And then an hour and a half in, it's like, oh, gotta climb this hill. And then the way down. I forgot to mention how long it took them to get to the top. So they climb another hill, which was about 100 feet for about 2 hours. So they're climbing it for about 2 hours. Then they went down the hill for that long. So I know it's a run-on sentence, but it describes it really well. And they get really specific with what's happening. I just want you to kind of just write about it. Interpret the domain and range of the function. So the domain is our time. So domain is from 0 to, how long were they up there? 7 hours? There were a few hours. Roading. How long are they? Oh, this doesn't say. Terrain represents the elevation in feet. Right, 2,000 feet of sea level for particular problems in the all right, from 0 to whenever they end, not specified. So it didn't specify when it would end. As far as the range goes, range is from the lowest point is about negative 6,000 from negative 3 times 2,000, so 6,000 feet below sea level to the biggest hill we said was 20,000 feet above sea level. So that's how you would describe your domain and range for the problem. The reason why I say this is obviously they're not going to go down until forever. It's just until they stop. All right, this is going to talk about the temperature in days. Use the table to determine key features. So what we're going to say is domain is a week of recording weather. Hottest temperature was 6 degrees Fahrenheit. I'm just going to put F. And lowest temperature was negative 3 degrees Fahrenheit. I didn't realize they were talking about the increasing and decreasing. So when we're talking about end behaviors, my apologies, we see here that it's starting to decrease. So this is increasing the more we go left. And the more we go right, this is starting to decrease. We went from 0 to -3. If we're talking about the middle, this is decreasing until we get to this 0, and then it decreases until like somewhere between 4 and 5. So let me kind of draw a graph. So it's decreasing, and then somewhere between 4 and 5, because this is a -2 and then goes back to -1, it starts to increase. It's going to touch that 0 and then come back down again. So there's our curves. We can talk about the zeros. This is actually a double zero because it touches it one way and it touches it the other way. And the end behaviors are as x goes to the left, as x approaches -infinity, y approaches infinity, and as x approaches positive infinity, y approaches -infinity. So seeing as how these two behaviors are backwards, this is an odd function. So we would be able to count the curves here. 1, 2, 3. For some reason, they don't tell us about counting the curves, but I mean, it's kind of implied when we talk about decreasing, increasing, and decreasing again. That's obviously 3 curves because that's where it's increasing and decreasing. Key features in the context. So, when we started recording, it was cooling down. It warmed a little, but then decreased again. So that's what we're doing on this one. Interpret the domain and range. Range is when we started keeping track of it. Range is day 1 of recording to 7th day of recording. Temp was from, what was it, 6 degrees was the highest? 6 degrees to -3 degrees during that time. And that's how you would phrase it with words. They're probably going to phrase it, oh, they actually did use words here. And they can use the notation here as well. They're using brackets because it did touch 1. It did touch 7. When did it touch 7? Did I miss that? I don't see when it ever got to 7. So I don't know where they got that 7 from. Oh, 7 days. This is the domain. So the domain is from day 1 to day 7, and then the range is from -3 to 6. Okay, that makes much more sense. Is there anything I didn't do? So I would give myself a 3. I forgot to write about n behaviors and zeros for some of the problems. So there I'm marking myself down for basically not reading directions. Let's go on to the next one. So this next one, we're going to be talking about graphing polynomial functions from equations. So we're going to talk about how to graph these functions using remainder theorem, synthetic division, and factoring. Factoring is going to help us out a lot for finding these zeros. Synthetic division is going to help us get to factoring. Remainder theorem is this idea. Remainder theorem and synthetic division kind of go together. So if the remainder is 0, that means we found a factor, essentially. If you need refreshers on this, you can watch my videos. Unfortunately, I don't edit these videos, so I can't put a title card. Or you can click remainder theorem and it can talk about it here. Basically, remainder theorem is just saying that, hey, if there's no remainder, that's a factor. Synthetic division, here's like the process of how to do it. They do it a little differently than I do. I like having my box this way. They have their box this way. I don't know why they have a box this way because they don't write any numbers on top. So that'll show you steps on how to do synthetic division. And factoring, we've done the X method, we've done the box method. So that shouldn't be too unfamiliar. So the first thing we're going to do here is they see like, hey, we can factor out by grouping. We can factor a 9 out here, and then we have the same factor here, which allows us to factor out that 2x minus 7. So they're factoring out this 2x minus 7, leaving this on the inside. From here, it's like, wait, we can factor this out. So they factor that out by taking out a 3x, and then we have these three factors. So we have x equals 0, and x equals, we're going to add 7 to both sides. So let me grab my pen. We're going to add 7 to both sides. We get 2x equals positive 7, so x is equal to 7 over 2. For this one, we're going to add 4. Let me use a different color. We're going to add 4 to both sides. Why am I explaining this? Edmentum's going to explain it right now. So they'll show you how to do it. They'll probably do all the steps at once, too. They did not. Oh, they did right here. Okay, so here's that. This is equal to 0. This is equal to 4, 7. So you can see right here how they found those zeros. Now we know our curves. So what we're going to do is we're going to test out a point that's bigger than our 0. This was one of our critical points. So we're going to try negative infinity. So we're just going to try a negative number. And when we do that, we get all of this stuff here. So as we do this, we get negative, 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 positive. They're basically just plugging in these factors into each one of these. So they actually kind of do it really interesting. So if you plug in, like, for example, a -1, this is negative. Plug in a -1, this is negative. Plug in a -1, this is negative. So a negative times a negative is a positive, times a negative again is a negative. So that's where they got this. This here is a positive. Positive times a negative is a negative, times a negative gives us a positive. So here, that's where we're plugging in something between 0 and this, which we'll probably try a 1. 1's the easiest thing to try out. So if we plug in a 1 here, we get a positive. If we plug in a 1 here, we get a negative. If we plug in a 1 here, we get a negative. So positive times a negative is a negative. A negative times a negative is a positive. This is a very interesting way of doing it because I always plugged into the whole function. They're like, hey, if we're multiplying, let's use the positive and negative rules. And that's actually pretty clever. I've never thought about doing that before. So because of that, we know that any negative number is going to result in a negative. And a number in between here and here, because these are our zeros, that means this is positive. This one's negative and positive. So it's important to test those out because we never know if we're ever going to get what I call a bounce. Because we know that it went from negative to positive, we know it's a 0. Sometimes because of bounces, we don't know if there's a negative going to a negative. We saw that kind of in that problem where they were keeping track of the weather and it was negative, it touched 0 and then bounced back down. So let's kind of take a look. So this helps us determine it. So if this is negative, we can see how the behaviors are. We also know that it was degree 1, 2, 3. 1, 2, 3. It was degree 3, so we knew that the end behaviors were going to be different. If it was an even degree, let's say degree 4, the end behaviors would be the same. So that's just a rough estimation. If we use the calculator, we can calculate a little bit more. If you guys need help, again, you guys can always make an appointment with me or leave a comment down below. All right, so let's talk about graphene. All right, so let's take a look, and I'm gonna try to start reading the problems here.